information. So I will send some homework problems on MDPs. So right after today, you would know value iteration, policy iteration, and you should work on those problems to make sure that you got it well. And also 2 papers that you would have to read for the, just like you read the landmarks, you will be reading 2 papers for the stochastic planning stuff. I'll send you those 2 papers too, and you are likely to have to write the reviews on one of them at least by next week. Okay, that's the heads up. So let's see. So we are kind of in the middle of value and in the middle of setting up the solution methods for Markov-Addition processes, right? So we are, I think this is the slide that I was at the end and then I kind of jumped ahead, so I'm just coming back to this. So you need to define, in order to decide what would be the policy, what would be the optimal policy, you need to sort of have a metric for comparing different policies, okay? And the idea for us is we will compare the policies in terms of the cumulative reward they will get you, okay? So you will talk in terms of the value of a policy. The value of a policy essentially will be defined in terms of if you continue executing that policy, okay, and if it's a finite horizon, you do it only for the horizon length. If it's infinite horizon, you'll keep doing it, okay, and then you can take the cumulative reward you're accumulating, and then you compare 2 different policies. Whichever has the higher cumulative reward, that's the one that wins, okay. That's the assumption. And we will also, it turns out that later on we will also see that while we actually are interested in the value of a policy, you can also talk about value of a state itself, okay. So the value of a state is the maximum cumulative reward. So you can define, we'll see that you can define value of a state in 2 different ways. One is value of a state with respect to a particular policy phi, which is if you start from this state and you keep following the policy starting from this state. Remember, the policy itself has to be defined for all the states. Okay, the policy itself has to be defined for all the states. Okay, it's just that you're starting from this particular state right now, and then you will do whatever the policy says is the action for this state. Whatever the policy says is the action for this state, and then you will get to a new state and you will collect the reward there, and then you also look into the policy table to see what's the action you are supposed to do in that state. And you keep doing this. If it's finite horizon, you do it just the horizon number of steps. If it's infinite horizon, you'll keep doing this and multiplying the reward you get by gamma power k, where k is the step, the number of steps you have already completed. Okay, and if you do this, then if you consider the cumulative reward you got starting from this state using this policy, then it's called the maximum value, the value for this state given the policy. Okay, and then you can also, just as you can talk about the value of a policy, you can also talk about optimal value of a state. Optimal value of a state would be essentially maximum overall policies, the maximum value that the state can have. Okay, and so, and in fact we will notice that in computing the optimal policy, you essentially compute the optimal value too. Okay, they are sort of duals of each other. Okay, that's basically what you wind up doing in the value iteration. Okay, and one thing that you want to keep in mind is the reward of a state and the value of a state are completely different. When are they same? when is the reward and the value of the state the same?
Sync state.
What?
Sync state.
Sync state is one way, or if it's a sync state, that means you can't do anything more, so what you get in this state is the value of this state. Another way is you essentially are in a finite horizon MDP with the horizon being 0. Do you see what I'm saying? So the timeout, this is it, and in which case whatever you get from this state is what you get. Okay, if you have 2 more days to live, then you consider what you got from this state plus what else you can get by doing the policy from there. Okay, so V star S and R of S are the same only when the horizon is 0. In fact, what we'll do in today's class is we'll first look at the finite horizon MDPs, which are actually easier to understand, even though they have a more complex looking policy, because there's a policy for each step to go, each time to go. Okay, and then we basically just generalize that to infinite horizon policies. The interesting theory actually is for the infinite horizon policy, infinite horizon MDPs, because it's not at all obvious that infinite horizon MDPs will have an optimal policy. And that's, I mean, assuming that you read the textbook, you know that that is the case, because in fact, and that there will be an optimum policy, and that you will get to that fixed point is because of the contraction operator. The Bellman update becomes the contraction operator. Okay, so so finite horizon value functions are easy. Basically, you can talk about the value function for, if you're given a particular policy. You normally, here I was talking about value of the state given the policy. Really, I can talk about value of the state given the policy and the number of steps I have left to go. Okay, and if in fact I'm talking about V by 0s, that means I have 0 steps left to go. In which case you do know that that is just R of S. Right? And then the basic idea is you will then compute. So you know, remember that in a finite horizon MDP you have a policy for each number of steps to go. So if you have a 3 horizon MDP, then you need a policy for 3 steps to go, 2 steps to go, 1 step to go, 0 steps to go. Okay, when you have 0 steps to go, you already know the value function. When you have 0 steps to go, you have no action to be done. Okay, but if you know the V0 of S, then I can compute the value of 1 step left to go. I can compute the value with 1 step left to go, and I can use that to essentially basically compute. So we'll talk about 2 different issues. One is, given a policy, how do you compute the values of the states with respect to that policy with different number of steps left to go. Okay, and starting from that, we can also talk about directly computing the optimal value and then converting it to the optimal policy. Okay. So for the finite horizon problems, value depends upon the stage to go. Okay. So if you are talking about the value of this state with respect to a policy pi with k steps to go, that would be essentially expected value of the following, which is you have k steps to go, so you can make k times you look into the policy table and do the action that it says for the current state and then collect the reward. Okay, in the finite horizon case, we assume that the rewards are just added up. You don't need to discount them. There's no reason to discount them. Okay, one interesting funny thing of course is, remember we gave some sort of a psychological validity for discounted rewards. That psychological validity would have worked even for finite horizon case if the finite horizon is a very long finite horizon. It's just that, you know, mostly in the formal models, people tend to just assume that you will add up the rewards if it's finite horizon. And if in fact you want to discount, nothing really changes. You understand what I'm saying? So even if you want to discount, even though you have finite horizon, you want to discount the reward one step away by gamma times the reward you get there, that's okay. It'll still work. Okay. Okay, so all I'm saying is, in this case, is you just take the reward that you get for the p time steps, and while you are following this policy, okay, and if you want to rewrite that, that's essentially, since the reward is directly from the state in the simple model, reward directly depends only on the state. So you are basically saying, I'm starting from s equal to the beginning state as 0, okay, and then I'm picking action A based on what the policy says I should be picking for the current state, given that I have those many steps left to go. In the beginning I have k steps left to go, one after that I have k minus 1 steps, one after that I have k minus 2 steps, after k steps I have only 0 steps left. Okay, so that's what this is doing, and then once I do that action, remember that the reward of the state itself is not horizon dependent. The policy is horizon dependent, but the reward and the transition function are not horizon dependent. Okay, so the actions do the same exact probability whether you do it in the very beginning of your life or in the very end of your life from a particular state. Okay, so that's why you essentially do that action, and then you will get into some state based on that action, and then you compute the reward. You just take that reward for that state, and then you're adding them up. Okay, and the expected value is taken because you have to, because of the probabilities, every time you do this, you get a slightly different cumulative reward. You're trying to compute the expected value over a large number of these. Any questions on this topic? Okay, so that's basically how you define the value for a policy. You're defining value for a policy this way. Okay, so this is, think of this as, if I give you a policy, you can convert it into value, and then it turns out that if you given a value, you can also convert it into a policy. That also we'll see it in a minute, and that's why they're duals of each other. If I give you one, you'll get the other. Okay. Okay, now actually this is telling you a procedural representation, essentially, as to, you start and then you keep doing these actions according to the policy and collecting the rewards, and then after one sequence is over, you sum it up, and then you redo this whole thing again, and you take the expectation over the summations. Okay, but you can also compute this. Vk pi can be computed recursively in terms of Vk minus 1 pi. That means the value of a policy with k steps to go can be computed if I can tell you, because of the Markov property, then I can, if I give you the value of this policy with k minus 1 steps to go, then you can compute the Vk. Okay, and this recursion will end at 0. And you do know that value of a policy with 0 steps to go is exactly the reward function. Okay, and then what I'll write is, I will write the Vk of pi in terms of using this equation. Essentially, I can actually rewrite the Vk of pi as essentially in terms of Vk minus 1 of pi times the transition and the reward functions. And in essence, all that this is saying essentially is, if you are trying to find out, if you are in a particular state and you're trying to find out what is its value with respect to the current policy, assuming I have k steps to live, then the policy tells me that because I'm in this state S, I should be doing the action pi of sk. Right? Because this is a finite horizon policy, and so it is actually indexed off of the state as well as number of steps to go. Okay, so this will be an action. And this whole thing is basically the probability that if you do this action in this state, you will get to S dash. That's a probability number. Okay, that's given as part of the problem. Okay, and if you were to actually reach S dash, then the question of course is, what do you get for reaching S dash? So the policy, the value of S with k steps to go is somehow determined by a value of S dash with k minus 1 steps to go. Because you only have k minus 1 steps left. So if I basically, I can just say, what I get by doing this is this probability times the k minus 1 to go value of S dash. S dash is considered a neighbor of S in the sense that by doing an action in S, you get to go to S dash. Okay, so a state's k step to go value depends on its neighbors k minus 1 step to go values. Okay, by the way, remember that you can be your own neighbor. Right? If you do an action, if there is a probability that when you do this action in this state, like remember when you are, let's say, in the grid world that I showed you earlier, if I'm here and I try to go this way, then there is a 0.8 probability that I will stay in this, actually 0.9 probability that I will stay here, right? Because the assumption is that in the direction I want to go, there is only 0.8 probability that I will go that side, and I will go 0.1 probability in the perpendicular directions. Now, the assumption also here is that if you try to hit the wall, you stay in the room. If you hit the wall, you stay in the room, and so this way you stay in this room, this way you stay in this room. So when I do this action in this state, I am 0.9 probable to stay in this state. Okay, so your value might depend on yourself. Except in the finite horizon case, your value depends, your k horizon value depends on your k minus horizon value, according to this equation. Okay. And then of course, because you are in this state, you get the reward for that state plus whatever else you can collect by doing the policy. So I was actually able to take this equation and rewrite this in this form, where I'm essentially saying Vk pi is connected to Vk minus 1 pi. And notice that everything else are numbers that you actually know as part of the problem. So this is just a set of equations. Do you see that? Okay, it's just a set of equations. Okay, and these set up. So basically, if I have a 3 horizon problem, then let's say I have 3 horizons. Now just to get the thing. So if I have 3 horizon problem and only 2 states, S1 and S2, in my entire world, okay, then I have the following, and I have a particular policy pi. Then I have the following variables: V pi 3 S1, V pi 3 S2, and V pi 2 S1, V pi 2 S2, V pi 1 S1, V pi 1 S2, V pi 0 S1, V pi 0 S2. Okay, these are the variables. It turns out that these 2 variables are written, there are equations connecting these 2 variables in terms of these 2 variables. And you have equations connecting these 2 variables in terms of these, and the equation connecting these 2 in terms of these. And these last 2 variables, you know the values. Because 0 steps to go, the value is the same as the reward. That's it. Okay? So that's how you compute the value of a policy. Okay, it turns out that even for the infinite horizon case, actually computing the value of a given policy is always just simultaneous equation solution. Okay, what's interesting, of course, is computing the optimal value, which is harder. Okay, So anyway, so in this case, we know how to compute the value Vk here. If in fact I'm supposed to, according to my policy, I get to do, when I'm in this state, I get to do an action with which 0.7 takes me here, 0.3 takes me here, then I know the values, Vk minus 1 values for this and this, 0.7 times that plus 0.3 times that is the number here. That's the value of this policy. Okay, what we want to now do is, so this, if I stop right here, then essentially I can just go through every policy, compute its value according to this, okay, and then compare them and see which is the best policy. Okay, however, what I'm going to actually do is, in fact, that's that way of doing it. In fact, as I made a mistake last time, and Randy is right, that way of doing it will require how many policies? You have to enumerate how many policies. Okay, the number of policies will be, there are A actions per state, there are S number of states, so there are A power S policies for each horizon. So there is A power S policies for K horizon, A power S policies again for K minus 1 horizon, A power S policies again for K minus 2 horizon. So this whole thing power K, which is A power SK policies. Okay, so you have, if you stop right now, you have to enumerate each of them and check their values and find the best, which is, you know, a dumb idea, it turns out, and because we have a much better idea. The only way you know something is a dumb idea is because you have a better idea, really, right? So anyway, this, so the interesting thing is that the optimal values of a state at k steps and k minus 1 steps to go have a relation. Okay, and you can use that to directly compute the optimal policy without having to enumerate all the policies. Okay, and what's that idea? The idea is, if I happen to somehow know the optimal value for the states S1 to S4, which is suppose there are 4 states in my MDP, and I somehow found out optimal value for T steps to go. Then I need to find out T plus 1 steps to go for this state. Okay, so that is not hard, it turns out. Basically what happens is, in the previous case, if you're trying to compute the value of this state with respect to a given policy, you just ask the policy what action you are supposed to do in this state, and just consider that action's probabilities. If you don't have a policy yet, then what you really are going to talk about is, in from S, what are all the actions you can do? Suppose in my domain, A1 and A2 are the only actions that I can do. Okay, so I will consider doing A1. Remember, as far as my policy is concerned, the policy has to either say A1 or A2 in S1. Okay, what should it say if it's an optimal policy? That's what I'm trying to compute. And the way I would do that is, if in fact optimal policy was picking A1, then it would have got this much value, because A1 will take 0.7 to this, 0.3 to this, 0.7 times this plus 0.3 times this is what you get by doing A1. And if you do A2, you get 0.4 times this plus 0.6 times this. When I say this, I mean the T steps to go value of these states, which I hope by now I have computed. Okay, so then here I can, now that I know the T step to go value of all these guys, I get to compute who is the right action to pick, as well as what the optimal value is for S. Because after all, the value of S is the reward of S plus whatever you get by doing the right action from here. If you do this action, you will get 0.7 times VTS1 plus 0.3 times VTS4. If you do this action, you get 0.4 times VTS2 plus 0.6 times VTS3. You compare which is the bigger one. Take max of those. Okay? So, essentially, this one will be, the orange one is this, the yellow one is this, I have to take the max of those two, add it to the R of S, I get Vt plus 1s. Okay? So this is the celebrated Bellman update, Bellman equation. In fact, it's also called Bellman update because when we actually go into infinite horizon value iteration, you update the value function by this. You know, you act as if, so here actually, we actually think in terms of t plus 1 steps to go, t steps to go, t minus 1 steps to go. In the infinite horizon case, you're just iterating on the true value of v. So ith iteration value will depend upon I minus 1th iteration value function. Okay, in that case you will call it an update, this case you call it an equation. Okay, but essentially the structure here is that if I know the value, the optimal value here, I know how to compute the optimal value t plus 1 steps to go. That's a huge advantage because I do know, it turns out, I do know the optimal value to go for 0 steps. Because V0 pi 1s is the same as V0 pi 2s is the same as V0 pi 3s. You understand what I'm saying? If you only have 0 steps to go, it doesn't matter which policy you are following. You have nothing to do. Right? So you know V0, because of which you know V1 using this. Because of this you do V2 using this. Now you are doing this V1, V2, etc. without subscripting it with respect to any policy pi. That means you are getting optimal values. That's the cute thing, right? Now, if I happen to know, so basically, now of course, you know, it's sort of, you kind of know this, if I do have the optimal value, then of course I still need to compute the optimal policy. But actually, in the finite horizon case, as you are computing the optimal value, you also computed the optimal policy, right? In fact, as you said, the value for Vt plus 1s is max of these two plus Rs. Now, whichever actually contributed to the max, that is the action you are supposed to be doing in S. Right? So you also computed the policy. But if you are lazy and when you are computing the value, you didn't keep track of those pointers, you can still redo this. You know, if I just give you Vt plus 1 and Vt, and then if I ask you in this state what should be the right action to do, I'll quickly do this and pick the one with the maximum locally. Okay? That's basically the way you compute the policy. Okay, so essentially it's the Markov property, the property that the transition depends only on the current state and the reward depends only on the current state, that essentially allows optimal substructure in the policy. That means the optimal policy up to k steps to go would be a superset of the optimal policy with k minus 1 steps to go. Do you understand what I'm saying? This optimal substructure policy is actually a very important idea. That's, you know, whenever, you know, when it sucks, when that property holds, you essentially get to do a lot more improvement in terms of the algorithms. Okay, so in A star shortest path algorithm, again you have the same sort of dynamic programming that Dijkstra's algorithm does. Right? For example, it knows that the goal nodes can be reached from themselves with 0 cost. And then you compute for each node, if you only in one step, how far are you from the goal node. Okay, and that analysis works again because it's optimal substructure. That means if in fact it turns out that the optimal path from S0 to SG contains SK, then the subpart of the path from SK to SG is also the shortest path from SK to SG. That is the optimal substructure. Okay, the same optimal substructure holds for the policy itself. Okay, if in fact a policy, if I, for example, with 7 steps to go, I have a policy pi, and that's the optimal, then if I only have 5 steps to go, then I just take the last 5 of that 7-step policy, 7-step to go policy. Do you understand what I'm saying? If that's the reason, because of that, you were able to avoid the dump method, which is essentially enumerate a power tn policies and evaluate each of them separately and just compute the policy directly. Okay, optimal policy directly. Okay, so that's it. So this is called value iteration, and you almost already know that V0 is known, and so because V0 is known, you know, this stuff, I can just remove pi's. Okay, so I know V0 S1 and V0 S2, because of which, using Bellman equations, I can compute V1 S1, V1 S2, because of which we can compute V2 S1, V2 S2, because of which you can compute V3 S1, V3 S2. And once I know the value, I know the policy. Okay? Any questions? Okay. So here is a picture in case you want a picture. In the beginning, V0, you know the values, the optimal V0 values. That is 0 steps to go. It's just the reward itself for the states. And then for V1, you will essentially compute for each state, you compute the max action. So here is one action, the orange action, here is the yellow action. Notice that because this is stochastic problem, each action is a hyperarc. If it's a deterministic problem, it would be a normal edge, hyper edge instead of normal edge. Okay, because essentially one action can get you to either this or this with different probabilities, and this orange action will get you to either this or this, and you don't get to decide which one you will actually get. Because of which you can only talk about expected value of doing this action. And essentially what you're doing is you can think of these values of the states also as utilities of the states. That is a long-term utility of being in this state. Because you are in this state, if you then do the right thing starting from this state, you get the value of that state. If you're going to, if you're going to be in this state for about 5 more steps, then you will get, if you do the optimal policy, the maximum value you can ever get out of this state is following the optimal policy, and whatever that gives you would be the value. And that's actually the Vk of S, with k steps to go. Okay. And then basically what you're doing when you're computing this expected value, and then taking the maximum, then essentially you're doing maximum expected utility. Maximum expected utility over the actions you have, and that's why there is, you keep seeing in this chapter and in general in the discussion of utility theory and in MDPs in particular, MEU, maximum expected utility. Okay, you do the action that has the maximum expected utility. Okay, do you see what I'm saying? Now, the reason you have to say MEU is because you believe it's a stochastic transition. Because it's a stochastic transition. If you believe that the nature is out to get you, you can't do MEU. Right? I mean, this is the whole point we were talking about last class. In a game tree, right, if I do this, in a chess game, suppose I make the following move, I make a silly move, wherein, my opponent, based on this move, has a whole bunch of options, one of which is to checkmate me and end the game, and a whole bunch of others is to ignore my stupid mistake and let me continue. Now obviously if you think in terms of probabilities, it looks like there's so many branches, and if my opponent is kind of sleepy, then it will be 1 over n probability for each of them. And so you might be thinking MEU, where's the expected value of this stupid move. But unfortunately, if your opponent is awake, you don't get to do MEU. You have to you have to assume that your opponent will pick the move that is maximally damaging to you. Do you understand what I'm saying? Suppose, if you are actually playing this game not against nature, but against an opponent, right? Then with 0.7 probability you go to S1, whose value from your point of view is, let's say, 70. And with point 3 you go to S4 whose value from your point of view is minus 100. If you are working against nature, then you just say 0.7 times 70 plus 0.3 times minus 100. That's the utility expected from this action. If on the other hand you are doing the same action against a rational person who knows the game just as well as you do, then the utility of this doing this action is minus 100. Because there is a problem, no, there is, you can go here or go here. You are thinking it can happen this way or this way, but you assume if your opponent is awake, then they will actually do the one that is most damaging to you. So that's why this is MEU, whereas in min-max you do actually risk averse, which is basically you assume that the adversarial agent will pick the action for you, will pick the outcome for you to make it the worst for you. Whereas nature, on the other hand, let any of those outcomes occur with those probabilities. Okay? That's it. And so then you will get V1, and then similarly I can get V2, similarly I get V3, and then when I have all of them, in fact, as I am computing these, I have also computed the optimal action for each of the states with k steps to go, and so I have computed this. Okay? Okay? And if you happen to have been given the valuations, then in basically to compute the optimum policy for each particular state with t steps to go is, consider the actions that are available there and compute which one is sending the higher expected utility, and that is the action you're supposed to be doing. Okay? Okay, so instead of actually having to deal with, as I said earlier, instead of actually having to deal with an exponential number of policies, which is exponential both in terms of number of states, n is the number of states, and threshold, which is the number of iterations you're going to live. Okay, instead of having to do that, basically what we are doing only takes t times a times n square. Okay. So it is still, so this, if you compare this to order of a power tn, this looks like a huge steal. But on the other hand, n, in this notation, n is the number of states. So you're doing n square processing. Okay, now planning, I said, is p-space complete. Normal planning is a cheaper problem than this. Because MDPs are more general than normal planning, right? So the question then, is planning? Why is planning supposedly worse than this? This is only polynomial. It's only polynomial because it's in n square. But I said planning is p-space complete. This is supposed to be a rhetorical question. And you're supposed to just smile at me and I move on, but I don't think it is rhetorical at all. It looks like. So why is planning p-space complete while MDP, which is a more general problem, polynomial? Yes, sir.
Because in this you're counting states and in planning you're counting instances.
Exactly. Okay. In fact, planning is also polynomial if you think in terms of number of states, because planning is finding shortest path. Shortest path, Dijkstra's algorithm works. And that's a polynomial in the number of states in the graph. Okay. The problem is we decided that the right input size is not the number of states but the number of state variables. If I give you n, so in fact planning, so in fact that's why instead of s in n, instead of n I should have really had s there. So it's s squared. It's square of the number of states, where states itself are 2 power, if you are looking at Boolean propositions, then 2 power number of propositions. And if you count the input in terms of number of propositions, if you count the input size in terms of number of propositions, then that's why it's not polynomial. And so is in that case MDP is also not polynomial. Okay, and so if you come to this world from planning world, you should be surprised at people celebrating the fact that that something is polynomial complexity when the polynomial is in number of states. Okay, it really it's just as hard. In fact, it's, in some cases it can be harder, but at least you don't have any worry because as to whether there is an inconsistency between simple planning, which is just finding a line plan, and Markov-Ratian process, which is finding optimal policy for each state. Okay, they are in the same. I mean, at least both are exponential, so we are happy. Exponential if you keep the parameter the same, they're both polynomial in the number of states, exponential in the number of literals, state variables. Okay. So is this good? It's not really good. Okay, which is why, whatever again I remember, this whole thing is graph search discussion. This is generalizing graph search to a scenario where you have stochastic actions and generalized rewards. Normal graph search has deterministic actions and it only has reach the following states. It doesn't have any trajectory constraints. It doesn't say you have to visit all these good states while reaching this final state. MDP in essence is saying that because it's giving reward in every state. And the good guys will visit all the interesting states on the way to the final state. Okay? And the other interesting thing is that you keep thinking about, because again you went ahead and read the infinite horizon case, which we'll start talking about. Till now we haven't talked about sync states, right? We did talk about sync states. You don't need sync states if you have finite horizon, because every state becomes sync state when you have 0 steps left. On the other hand, if you have infinite horizon, it does make sense to talk about sync states, although it's not required. It's not required that there should be sync states even in infinite horizon case. Okay, in fact we'll get to this point that while there is in the class, the two things we'll talk about are finite horizon, which is what we just talked about, and infinite horizon. Okay, and neither of them need sync states. Neither of them need sync states. Without sync states, you still will have all the properties of the optimal policies. The only thing that matters for infinite horizon is gamma, or they call it beta. The discount factor should be strictly less than 1. That's all that matters. Okay? And here, it's finite. So ultimately, when you have 0 steps to go, the only thing that you get is the reward. In between are a whole class of MDPs, we will talk about them, called indefinite horizon MDPs. An indefinite horizon MDP essentially is finite, but you don't know exactly how long each behavior is going to take. In the case of indefinite horizon MDPs, you have sync states. And the reason horizon ends is basically you keep living some arbitrary amount of time until you die. And when you die, you reach a state from which you are unable to come out. It's a black hole. So you need sync states when you have indefinite horizon MDPs. And in fact, we'll notice that planning problems, when they are modeled as MDP problems, oftentimes you model them as indefinite horizon MDPs. Because you assume goal states are sync states and death states are sync states. Okay? An advantage of indefinite horizon MDP is you don't need to do discounting. No need for discounting. Again, even if you don't have a need for discounting from a mathematical point of view, you may decide to keep the discount factor for psychological point of view. Which is what I was saying. Even in a finite horizon MDP, you might still want to have discounting of later horizon. So if you do that, it's no big deal. Nothing changes here. Instead, basically, you would just say max of 0.7 times gamma times V0S1, 0.3 times gamma times V0S4. It doesn't change what is the optimal action, it changes the value itself. Do you see what I'm saying? Yes, sir.
Are indefinite horizon MDPs, is episodic another term for the same thing?
No, that's a different issue actually. It's a different issue. No, that's not exactly the same. Yeah, all we are saying is that, you know, when you start behaving from a particular state, when you simulate behavior from a particular state using a policy, you would eventually end in a sync state. Which actually, by the way, it turns out that when you have indefinite horizon MDPs, that means you have sync states. You can also have policies which will never end. You saw that in the first day's class, right? I mean, if you go back, you know, when you know, essentially the normal states are fun. This is an indefinite horizon MDP, right? Because it has sync states, right? Okay, and this is a case where reward for every state was greater than 0. Okay, and there are two sync states, and it turns out in this particular case that there are policies like this, and in fact the optimal policy in this particular case is never to end. And if you don't discount this, then essentially you're going to get infinite reward. Okay, so in fact one thing that we talk about when we have indefinite horizon MDPs is what is called a proper policy. I mean, again, think about, you know, you doing this in your church in front of your pastor or your imam or your whatever, you know, they're saying you should be worried about heaven and hell, and you're saying, no, I'm having too much fun. I'm not going to worry about it. Then they'll say, you can't live forever, you know, you're supposed to be a proper person. Okay, a proper policy is one which with 1.0 probability reaches a sync state in any single simulation. Do you understand what I'm saying? So this is not a proper policy, because if you follow this policy you will never reach any sync state. Okay, and whereas all others are proper policies, because with 1.0 probability you will reach a sync state. And you would be searching, just a second, you will be essentially for the indefinite horizon MDPs, you will be searching in the space of proper policies. Yes, sir?
Is it probability 1 or all paths terminate?
No, not all paths terminate. It's with probability 1 you will eventually reach, with infinite number of steps, you will reach the sync state with probability 1. That's all. So if I start, you know, if I start with this, right? If I start from here, I start following this policy. All I am saying is, infinite number of steps, you will die either here or here. You ask me exactly how many steps, I don't know. I can have an expectation on it, but it's going to be finite. Whereas for this, it's not finite. She'll never reach. You will never ever reach, a sync state. So indefinite horizon MDPs are sort of between this and this. We will be talking about these two because they're easier to understand up front. But I am giving you a heads up that actually most of the time when you connect MDPs to the kind of planning problems we saw, where goals of attainment, okay, are if you, for example, there is a classic version of MDP called stochastic shortest path algorithms, stochastic shortest path problem. Okay, where essentially assume that every one of these states gives you small negative reward. I'm sorry, no, you can think in terms of costs. Okay, every one of these things gives you negative reward. These two are sync states; they'll give you 0 reward. So the optimal, what you're trying to find is what is essentially the shortest path to get to one of the end states. It's like a path planning problem, except now you are stuck with stochastic actions instead of normal actions. And stochastic path planning problem is a classic indefinite horizon problem. Okay, and if for an indefinite horizon problem, if the rewards are not properly set up, you might allow improper policies. If you allow improper policies, you then have to discount. Otherwise, you cannot compare policies. All improper policies are equally good because they're all infinities. Right? Okay. I mean, especially if you have in this case. In this case, all the improper policies of this type all have infinite expected cumulative reward starting from any state. Because they'll never die and they'll keep just eating more and more positive reward. Okay? Okay. So this is the summary of the finite horizon. By the way, this is an interesting point to keep in mind. Optimal value function is unique because optimal value function is computed by the set of these equations. They will be unique. Optimal policy, on the other hand, doesn't have to be unique because two actions can have the same expected utility, so you pick any of them. Okay? Many policies can have the same value. Okay, so defining value as the, now if you go to the infinite horizon, we'll just cross over and go to infinite horizon. And so all of these kinds of MDPs are used in some case or other, in OR literature, in the operations research literature. Okay, finite horizon MDPs are used more often. Okay, and in fact, one of the interesting things is if you take operations research number 2 course, typically they will teach you MDPs. And they'll teach you MDPs where the number of states is of the order of tens of states. And so if you have an order of tens of states, then you set up a finite horizon MDP, it's not hard to solve, it's 10 square complexity. Our problem is we have hundreds of state variables, which means 2 power hundreds of states. And you do 2 power 100 square processing and you die. Do you understand what I'm saying? So OR guys would not understand why the heck are you guys so upset about MDPs. We can solve them, well, they can solve 8-state MDP problems normally. And they, in fact, in MDP, in OR literature, OR textbooks, you're supposed to, if I'll give you a homework in the exam, you will write this entire, you could have done this on a sheet of paper, right? So that's the sort of level of size of problems that you wanted to do. I mean, not very small, but tens of states is what you wind up looking at, where the state of the problem is manually abstracted such that the number of states for the problem is very small. So you consider you remove many irrelevant details and say only these are actually important. There really are only 8 different states. And then you can do MDP on top of that. Okay, so that's where finite horizon is used a lot in that. In the context of planning, where do you use finite horizon MDPs? In the context of classical planning. Remember, MDPs is supposed to be general case of classical planning. So where can we use finite horizon MDPs in planning? Yes? Yes, classical planning doesn't have time limit. When you say time limit, there's a big worry as to, are you talking about CPU time limit or the plan execution time limit? Which one do you have in mind?
I was thinking of CPU.
No, CPU time limit, don't even consider that, because by improving the algorithm, you can change the CPU time limit. Okay, you are on the right track as long as the word time is concerned. Suppose you are considering bounded length planning problems, which is what graph plan does. What is the optimal plan? So think of graph plan, think of the following scenario. Think of graph plan with non-uniform cost actions. With non-uniform cost actions. Okay, finding an optimal plan essentially of size k. What is the k action plan which has the lowest cost? Then k becomes the horizon. Okay, so that's where planning is connected to finite horizon. So you somehow artificially said, I only am going to do k actions. So what is the cheapest sequence of actions I can do to reach the goal? Okay, and in fact, I can also actually, in the context of MDP, I can also consider problems where instead of G1, let's say my goals of the original problem are G1 to Gn. And normally in classical planning, you have to achieve all of them. If you achieve G1 to Gn minus 1 and didn't achieve Gn, you get 0. Okay, but that's like being too harsh, right? You know, when you do an exam, if you do as many problems as you can before the time is over, and I give you partial credit, right? Then the question is, which problem should I concentrate on? Given that I only have this much time to write my exam, forget about thinking, let's assume you don't think during exam. This much time to write my exam, which problem should I concentrate on to maximize my reward, which hopefully is the cumulative mark you get on the exam? That's an oversubscription planning problem. That's a slightly more general problem than classical planning. In fact, people hate it when they have to make that decision. You know, it'll be much easier. In fact, I cannot understand this. I mean, I always did this because I've taken probably too many exams in my life. When somebody gives me an exam paper, it has been at least 30 years since anybody gave me one. But when they used to give me exam papers, I would actually open all the pages to see where the easy problems are and start working on them first. Or at least know that they are there so that if I'm running out of time, I'll work on them. Every year, every semester, when I give exams to students here, I tell them, you know, please look at the entire exam before starting to do it. Would they do it? No. Time, right away start writing from the first line. So if I give you the hardest problem as the first problem, you all fail. Because you wasted all your time trying to do the first problem, you know. And because we assume that somebody else made our life simple and easy problems are first, harder problems are later. That is true in some standardized tests. So for example, you know, like GRE supposedly does that. Math counts, for example, always has this, you know, math counts is this, you know, math Olympiad kind of a thing. They always make easy problems up front, harder problems later, because presumably they think middle school kids can't think, deliberate as to where the easy problems are, the hard problems are. Okay. But in general, you know, oversubscription planning is slightly harder because you're actually first trying to decide where the easy problems are and then work on them. It turns out that problem can also be written as a finite horizon MDP. So if you have a graph plan scenario where you're looking for k-step plan which gets me the largest reward, where all the goals have their rewards and I need to pick some subset of goals and actually try to achieve them. What's the optimal plan then? You can write this as an MDP, finite horizon MDP, and it will solve it. Okay, so that's where that's useful with respect to planning. Infinite horizon problems, models are used more often in the reinforcement learning community, because you assume that the agent will keep on living, and in fact the difference, by the way, we'll get to that in a minute, not a minute, but in a couple of classes later, but the difference between reinforcement learning and Markov-Adhesion processes is, in the case of Markov-Adhesion processes, everything is given to you, even though it looks as if everything had to be computed from scratch, but you are given the reward numbers, you are given the transition probabilities, those two are given for you. Okay, giving the transition probabilities is called the model of the problem. That's given to you as part of MDP specification. Giving the rewards also is the reward model of the problem. This is the transition model, this is the reward model. They're both given. In which case, finding the optimal policy is a pure inference problem. In the real world, when we are actually looking at an unknown world, then what happens is you try certain actions. All you know is what actions can you do. So if you're a kid, right, you do know that you can put your hand everywhere, like this, and you can also eat a couple of things. Okay? And so, and then when there's a nice red stove, for some reason I keep thinking about it, you'll put your hand on it and you will burn your hand. Then if you have a brain, you will say, that doesn't look like a good thing to do. Okay? And then you basically avoid doing that later. So in some sense, you are learning the transition model and also reward model actually of the world. That's reinforcement learning problem. Okay? Since kids, in terms of the number of actions they get to do, basically live infinite number of, with sync states, of course. You can also burn yourself, but but they do live infinite number. They do get to do infinite number of primitive actions. So it makes sense to think of infinite horizon MDPs in thinking of reinforcement learning. For most normal planning problems like stochastic shortest path, etc., we will look at indefinite horizon MDPs. Okay, so let's look at the infinite horizon MDPs now. In the case of that, basically that's where you need to do discounting, otherwise you die. Otherwise you die in the sense all the policies will be, there's nothing to differentiate one policy from other because they'll all be equally good if there's no discounting. Because they will all wind up getting plus infinities and minus infinities as the cumulative reward, and so you can't differentiate. Okay, so you will wind up putting a discount factor beta and beta less than 1, and in some sense, if you're trying to combine, you're trying to get your horizon, you're trying to get your intuitions from finite horizon MDP to infinite horizon MDP, then beta is connected to the effective horizon. You may not know the exact number, but beta is connected to the effective horizon. So, which is large horizon, which is small horizon? For beta equal to 0, is that large or small horizon? You agreed with me when I said beta is connected to the horizon. Okay, if I put discount factor close to 0, then am I essentially solving a low horizon problem or a high horizon problem? Low horizon problem. The people who drop out of elementary school are solving beta close to 0, and they're solving low horizon problem. If you put beta close to 1, you are solving very high horizon problem. Very high horizon problem. So now think about this. If in fact beta is changing, essentially, if you have a finite horizon, you do this with 0, 1, 2, etc., all the way to the effective horizon. And you compute, and you have the V0s, then you'll do the V1, V2, etc., up to Vk, where k is the total number of steps you have. And I basically told you that gamma close to 0 means k is close to 0, effectively. Gamma close to 1 means k is close to infinity, effectively. Which means, even before actually getting to how you solve the optimal policy problem for infinite horizon case, which do you think will take longer time to compute? Again, do the dimensionality analysis. If beta equal to 0, then you're done. Reward is essentially the only thing you get. The immediate reward is the only thing you get if beta equal to 0. So which means you can compute the optimal policy very fast. Okay, now unfortunately, the beta is something that you are picking. It's not the problem that is giving the beta to you. Okay, the world as a whole is made the same way for you who are stuck here in the PhD program, and the kid who at the current right now is deciding, oh, I had enough studies, let me start working right now. The world is the same for them. The environments are basically, the overall world is the same, but you are picking different betas by yourself. So if you make problem simple by picking beta equal to 0, that doesn't mean that you are getting the optimal value out of it. Do you understand what I'm saying? Okay, and in fact you will see that, no, obviously you read value iteration for infinite horizon problems, right? And the number of, the time taken for value iteration to converge is hugely dependent on the beta value. If beta is close to 0, it converges very fast. If beta is close to 1, it doesn't converge. Okay, in fact, there's a picture in the textbook which looks like this. So if you are considering for an epsilon for a particular amount of error, okay, and this is the y-axis is number of iterations before the value function has reached that level of error. That means vi plus 1 minus vi is only epsilon away, right? And the question is, here are the beta values, 0, blah, 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 up to 1, 2, you can increase it up to more than 2, 1, 2, and they'll all look like this. because at 1 they don't converge. Okay, and obviously as I increase my error, as I make my error threshold to be more and more tight, then, so this is epsilon equal to, let's say, 0.01, this might be epsilon equal to 0.1. That's basically how the iterations work, and you can essentially understand what Infinite Horizon MDP is doing as running this until Vk and Vk plus 1 are the same, or they are no longer different from each other. In which case you stop and say that is the only value. Do you understand what I'm saying? So because for the Infinite Horizon case, there is actually no point in talking about value with k steps to go versus value with k plus 1 steps to go. There is steps is always infinite. So there really should be only one value function, one optimal value function. However, you can compute that optimal value function, okay, by essentially using this approach. The only thing you need is what do you put at, what does V0, V1, V2, V3 mean if in fact the number of steps doesn't matter. It's just a computational. It's like the index I. V0 iteration, the first iteration I set the value function to be some random values. In fact, normally what you would do, most MDP algorithms do, is to set the value function to be the reward value. That's what they do. Which is essentially what you would have done in the Finite Horizon case too. Although you will notice later on that actually a much smarter idea is to set the value function to be closer to what its eventual optimal value would be. And so in fact you can, just as A star search can be speeded up with admissible heuristics, if I give you in the, if I give you an MDP, Infinite Horizon MDP, and I set the original value function to be V star itself, then in one iteration I will converge. So if I have some rich uncle who gives me close to V star, which is like giving close to H star. And notice again, heuristics and values are very similar. They're actually the same. Because just, heuristics, even if you want to go from start state to goal state, you need heuristic value for every possible state in the world. You might say, no, all I need is like these 15 things that will eventually occur on my shortest path from the short state to goal state. But I don't know which are those 15 things, because of which I need the heuristic value for every possible state. And then I use that to improve my search for this path. Okay, and so in the Infinite Horizon MDP case too, if I start by initializing my first values, a guess, to be closer to V star somehow, then I'm likely to do much fewer than these many iterations. And when in one of the papers, in fact, you will be reading for next week, that's more or less what they do. They basically take a simple value iteration and then they'll use planning graph heuristic, believe it or not. This is like you thought you forgot about that. Planning graph heuristic to set the value for the initial values for the states. And then let that Bellman figure out the real values. Okay, now whatever the valuations here are, if you start doing Bellman update, okay, between Vk and Vk plus 1, you can see whether the value functions are different. Now the normal distance function you take between value functions is max norm. That means the maximum difference between any two corresponding values of a state. So that means for each state, you compute what is Vk plus 1s and Vks. Okay, take the difference. And you take the maximum of all these differences, absolute value maximum. That is the true difference, that's the maximum difference, that's the difference. That's considered the distance between these two vectors. And the epsilon essentially says keep going until the max norm is less than or equal to epsilon. Okay, and of course we have, the reason as to why as you keep going you will eventually reach any epsilon is because of the contraction property that you again read in the book. We'll probably say it again next class, but you already read that. And what a contraction operator is really is it's an operator which keeps making two quantities come closer and closer and closer in terms of some distance metric. So the simple case is if I give you two numeric variables, let's say two positive numeric variables x and y, the operator divide by 2 is a contraction operator. So x minus y is one number. X by 2 minus y by 2 is another number, but that's smaller. X by 4 minus y by 4 is another number, that's even smaller. X by infinity minus y by infinity will be eventually 0. Okay? So that's a contraction operator, for example. And what you need to convince yourself really is in terms of, here the distance is defined as the difference between x and absolute difference between x and y. Now, instead of x and y, I have value function 1, which is a vector, value function 2, which is a vector, and instead of half, I have Bellman operator. Okay, and you need to convince yourself that actually it does contract. That means every time the distance, the maximum distance between the two vectors is reduced by a factor of beta. So as long as beta is less than 1, you know that you are contracting. If it is greater than 1, God help you, because you actually diverge. Okay? But, so that's the mathematical way of looking as to why this actually converges. But you can also see what the value iteration process is doing as setting up a pseudo finite horizon, where you stop going back and back. Here you knew how many, the loop was loop k equal to 0 to, I equal to 0 to k is the way this loop was written. In your case, you will just say repeat until the difference between the two vectors is less than epsilon. So it's basically the same exact idea. Same exact idea. But for it to work, you needed the discount factor. And for you to prove that it actually works, you need to understand that the Bellman update is doing contraction. Okay? And let's see. So, and one other thing, of course, is the V star itself, the optimal value itself is not horizon dependent. As I said, we just assume you only have one V. It doesn't, you no longer index it by the number of steps, because the number of steps is always infinite. If you have infinite steps to live, you did one step, you still have infinite steps to live. Right? So that's why you just think in terms of a single value function. Okay, apparently I stopped myself, but so, we'll come back next class. We'll also talk about policy evaluation, which makes sense for infinite horizon MDPs, where you directly search in the space of policies rather than this, which is searching in the space of values. So I want you to at least remember that value iteration for infinite horizon MDPs is really value iteration for finite horizon MDPs, where you convert a loop from I equal to 0 to k to a repeat until the distance between the two vectors is less than epsilon. And you are doing exactly this computation. The only difference is when you say 0.7 times V0S1, you will say 0.7 times gamma times V0S1, 0.3 times gamma times V0S4. So in fact, what you actually do is RS4 plus gamma times max of these two. Okay, that changes the value you get in the next iteration, but it doesn't change actually the action. But remember that in the infinite horizon case, you don't keep picking the actions until the value function actually converges. And once the value function converges, then you assume that the right action to do in any state is the same, irrespective of what time you ask that question. Because you assume you have infinite amount of time. Which means if you ask me what was the right action to do in this state yesterday versus you ask me again today, I will still say the same thing. So finally, in the infinite horizon case, the policy is also stationary. Already transition function was stationary, reward is stationary, but in this case even the policy and value are stationary. Because infinity minus 1 is infinity, that's why. Okay? We will talk about value policy iteration and then go into much more of this kind of a discussion, which is, in particular, we'll look at, when we come back, we'll look at this slide, which is, next one, examples of MDPs. These are all special cases of the general MDP model. Each has a slightly different property. Just as you have finite horizon, infinite horizon, you can also have cost-based models, reward-based models, cost and reward-based models, and then you can talk about things like models which have sync states in them, models which don't have sync states in them, and then talk about how these ideas can be extended to any of those MDP models. Okay, and then we will eventually get to next week also to doing stochastic planning using MDPs.